point signal, and that capital N can be anything starting with 1, 2 like that, but it should be sufficiently large, and usually we take it to be a power of 2 for convenience in hand. Usually we take capital N to be a power of 2, 4, 8, 16, 32 like that. So the sequence which we had discussed in earlier discussion, we were just discussing xn and cap and small n, which was the index, was allowed to vary between minus infinity to plus infinity, but this is also just theoretical with no significant application or realization. What is completely doable is a signal xn for the range 0 and n minus 1. So a sequence, a discrete sequence x small n, where small n is the index, which is equal to 0 to capital N minus 1, is available to us and it can be processed. So signal processing in general, most of the times is limited on this. Usually 16 point signal, x0 to x15, x0 to x31, 32 point signal, like that. So the question now is transforms of this signal. And now we were talking about discrete time Fourier transform. We were talking about discrete time Fourier transform, but this discussion was essential because discrete time Fourier transform or Z transform can be for any sequences. Sequence can be finite, sequence can be infinite, but for infinite sequence, its application is not there, and also it is not possible to discretize the transform. So if we now focus our attention on discrete time Fourier transform of a finite sequence or capital N point sequence, if we focus our attention on DTFT. What is DTFT now? What is the formula? X of x of e raised to j omega, or in general it can be said as omega also. X of omega is equal to summation, that we should use that of xn e raised to minus j omega n, and n was ranging from minus infinity to infinity. Now for a finite sequence, it will range from 0 to n
minus 1.
0 to capital N minus 1, right? X, is it clear now? A discrete time Fourier transform, a discrete time Fourier transform of a finite sequence is represented like this. But discrete time Fourier transform x of omega is continuous in nature. Agreed or not? And therefore it cannot be handled by computer. Now the question is it possible to represent this x of omega by finite number of samples? Can this x of omega be made such that it can be understood by a computer program? Are you getting me? X of omega, discrete time Fourier transform, is a two-dimensional function of omega, and omega is range bound between 0 to 2 pi. So x of omega has got two components, either xr omega and xi omega, or magnitude of omega and phase of omega. Are you getting me? x of omega is a two-dimensional function of omega. Omega is a continuous variable, but it's a range-bound continuous variable, because if it goes beyond the range, then x omega repeats. X of omega is a two-dimensional repetitive continuous function of continuous variable omega. I again repeat, x of omega is a continuous repetitive two-dimensional function of continuous variable omega. So at least you should fully understand this, or everybody at least must recite this, so that every time when you wake up you should recite x of omega is a two-dimensional continuous repetitive function of continuous variable omega with repetition of interval 2 pi. This two-dimensional function can be represented by xr omega and xi omega, or it can be represented by mod x omega and phi of x omega. Right. But the problem is that being continuous, it can't be understood by computer. Then, if it is to be made understood by computer, it should be digitized. Means it should be discretized first. Now the question is, can this continuous function be discretized and fully represented by few points? What we have? We have x of n. How many points are there for the period 0 to n minus 1? Or we have x of n point sequence xn. We have n point sequence xn, right? It's transform. It is dtft. Is x of omega is a continuous function. dtft is invertible. If dtft exists, when it exists,
solution less than infinity.
x of n is absolutely summable, or its Z transform is such that ROC includes unit circle. But for finite sequence, this question is not arising. If xn is finite, and bounded, obviously, if xn is bounded and finite, then it is absolutely summable. So its the Z transform will include the unit circle and ROC, right? So DTFT will exist. If DTFT exists, it is invertible. Means we have not studied inverse of DTFT finding yet, but IDTFT is this, right? IDTFT is this. Okay. Now, what I want, the question is whether this x of omega can be discretized. Discretized means this is infinite right now, infinite points omega. Omega is finite interval, by finite interval 0 to pi, after that it repeats, but infinite points. Can it be discretized such that only finite points are there? Means, can I make it xk? Can I take only few samples of x of omega as xk? Then the answer is obviously yes. Why? My question is an obvious answer. Can I take finite points? Obviously yes. Means it is just like a question whether the for absent student, if the task given to him is that you go to a student who was present and try to know the things which were discussed in the class. Obviously, the thing is that he is not going to get everything, but he will take few samples. Then can he take few samples? Yes, he will take only one sample. Now, but the question is whether these few can x of omega be represented by discrete finite. This is having infinite points. Why? Because it's a continuous function. Can it be represented by finite points with discretization? Discretization such that entire information of x of omega is preserved in this. Are you getting me? We are discretizing. Discretizing is a simple process. Just you have to collect. Whether that collection is sufficient or not will depend upon, from this you can get this, but from this can you get this? Means 2 plus 3 equal to 5. Means from 2 and 3 you can get 5, but from 5 you don't get this, because there are multiple options. So discretization is a simple process. Is it invertible? Can you sample such that? Can you arrange a method of discretization in such a manner that it is invertible? From this, can you find this? Its direct answer is difficult to be given. From asking you to design something from discrete to continuous is very difficult, but its indirect answer can very well be given. These are endpoints. These are, let us say, also endpoints. Also, it can be more, but it can be less. Suppose that if you collect n equally spaced samples at an interval of 2 pi by n, kth sample is, first is at omega equal to 0, next is at omega equal to 2 pi by n, next is at omega equal to 2 pi into 2 by n, or 2 pi k by n, each sample. If you collect n samples, then you will be having this n point. So it is n point sequence, it is n point DFT. But from this, can you construct this? You can't answer directly. From this, can you construct this? Yes, you have constructed. From this, you can construct this. From this, you have sampled this. The question, are you getting me? From n point sequence, you have found out DTFT. From DTFT, you have found DFT. This process is sufficient or not? Whether this DFT completely represents the DTFT or not? Because DTFT is continuous, DFT is discrete. Whether my sampling is complete or not, sufficient or not, that can be answered only if this is invertible. But from this, can I find this is a difficult question to be answered in a direct way. So, can you have, by some indirect mechanism, answer this question? So, from this you can find this, from this you can find this, directly you can bypass this, and from this you can find this also, by bypassing this. Then, if from this you are also able to find this, then it is obvious that this sampling is sufficient, because from this you found this, from this you again got back this, and from this you can find this. Means that from this you can find this. From sequence you find DTFT, from DTFT you find DFT. The question was whether DTFT to DFT sampling was sufficient or not, that is invertible or not. That question can't be directly answered. But if you have idea to find from DFT the original sequence, in that case, you can DTFT can be found from sequence. DFT is found from DTFT. From DFT, if you are able to find the sequence itself, it is obvious and but natural that from DFT, you can find DTFT. So it is an invertible process. And it is such that if you are having n points and you find n point DFT, it is very much obvious. And what is the formula for DFT then? X of omega is DTFT. What is x of k? At omega equal to 2 pi k by n. So the formula is like this. We end with this formula. X of k is equal to n equal to 0 to capital N minus 1. This is an n point sequence. K is starting from 0 to capital N minus 1 also. Means k between 0 to x of n e raised to minus j 2 pi upon n into because
Okay.
this omega is and e raised to minus j 2 pi upon n is difficult to be remembered every time. Therefore, it is n equal to 0 to n minus 1 x of n wn raised to you can have kn. This omega is 2 pi by n k and this wn is a shorter representation because it is difficult to remember. So wn is a two-dimensional variable. So x of k is discrete Fourier transform. Xk is discrete Fourier transform and is naturally invertible, and its inverse you can find. So we'll meet tomorrow at